Hello and welcome, honor students. Yesterday we went through 15.1 and we talked about water, we talked about the Lewis structure, we talked about how in fact it's held together and why water has some of the specific properties that it has, specifically because of the hydrogen bonding, and that gives it its low vapor pressure and its high, unusually high boiling point, and also the property of water in its solid state, ice, and how it is less dense than liquid and floats. So we're going to actually build on that today and talk about homogeneous mixtures and homogeneous aqueous systems. So that is 15.2. So we're going to do part of 15.2 today, and I'll finish this one up on our virtual lesson on Monday. So this will be part A. So let's talk about this here real quick. How can you make a pickle glow? So we're going to look at a pickle inside of a solution is got salt and brine and other things that are spices and solutes that are dissolved in the solvent. And we're going to talk about those terms in this lesson. So although it sounds absurd, an ordinary dill pickle from the deli can be a source of light when connected to electrodes. So you can see here in this illustration, they have electrodes and then they have a energy source right there. And you can see right there a glow. Why is that happening? Now that pickle has a large percent of water in it, and that's what we're going to talk about in this lesson. So solution. So think about a solution. What type of substance dissolves most readily in water? So first off, we talked about a homogeneous mixture. A homogeneous mixture, if you remember, is a solution. So that's another name for it. It's a solution. It's said to be one phase, and that's a key word there. It is uniform throughout. So when you are looking at it, it is not. So if we had some type of a container right here and we have one phase, we don't see any areas of different appearance. That's a solution. Now, if you saw little clusters of some things here and maybe something sitting on the bottom over here, and maybe it's a little foggy up in this section right here, now you have a mixture. So there's particles maybe floating, some things in there. That's a heterogeneous mixture, and we're going to talk about those on Monday. So an aqueous solution, so another term for us. An aqueous solution is water that contains dissolved substances, water that contains dissolved substances. So I'm going to be referring to some little demos I did earlier in the year. Hopefully you remember that, where I had a beaker and I had some distilled water, deionized water, and I took the little electrode, if you remember, hopefully you remember this, I took the little electrode and I inserted the wires into the water and nothing happened. It was no flow at all, no current flow through that distilled water. Hopefully you remember then I took that same beaker and I added some sugar, some C6H12O6, and that is a molecule. It's a nonpolar molecule. So I dumped this into, let it stir up, swirled it, and then stuck the electrodes in it. Hopefully you remember what happened. Nothing. There was no current flow. And then I took that same container and I added NaCl. And now we had a current. So it was a ionic compound. And I've done this, actually I did this a couple of times throughout the course of the year. In one of the other activities, I use potassium chloride, KCl, and it did the same thing. We saw a current flow. We're going to talk about that today. So let's get a few terms. You heard me use them at the beginning of this lesson. Really important. Please get them in your notes. In a solution, the large amount what is going to have something added to it is the solvent. So the solvent is the dissolving medium. In most cases, it's water. You may have heard me use this expression a lot of times. Water is referred to as a universal solvent. That's one way to kind of remember this. So what's doing the dissolving is the solvent. What you're adding is the solute. So when I mentioned sugar, that's the solute that was going in. When I mentioned sodium chloride, that's the solute. When I mentioned potassium chloride, that was the solute. So it is what is being added to the solvent. That is your solute. Real key terms there. Please, hopefully you got those in your notes. So a solvent dissolves the solute. The solute becomes dispersed all throughout. If you talk about a solution, it is evenly distributed throughout. And you may not be able to see it. For example, if you add sugar or you add salt to water, you're not going to be able to see it. But if you added copper chloride to water, now you will have a solution, but that solution will be a nice blue color. So just because it is clear or there's a color doesn't discount that you might have a solution, because they're all solution. When you talk about copper chloride or copper sulfate has that blue color, it is a solution as well. So a solution is a homogeneous mixture. We mentioned that already, and it's said to be one phase. If you were to take a filter, and that's what this is talking about right here, if you were to take a filter, just take this little thing here and say that's a filter, and you pour it through, it's going to come out and go into a container, and it will not separate. Please make sure you remember. We talked about this and we did this demo earlier in the year. The only way you're going to separate a solution is by letting it evaporate or by distillation. So you could distill the solvent off, and then you would end up with, for example, with salt, you'd end up with the salt crystals in a container, whatever you were boiling it in. So that is real important. So key concepts: substances that dissolve most readily in water include ionic compounds and polar compounds, really key. So ionic compounds dissolve in water. We talked about that when we were in chapter 7. Water has the ability to surround and pull apart. Even though it is a very stable form and requires a tremendous amount of heat, water can gather around it. So if we said, instead of sodium chloride, let's say potassium chloride. So we know that's made up of potassium 1+ and Cl 1-. What water does is it surrounds and pulls it apart. So what you're going to get on this side around this potassium is the oxygens, just like so. And the oxygens have that slight negative charge. This is positive, that's what the ion is, and it's going to pull away from the chloride. So now you're going to have the potassium 1+ with all these water, the oxygen parts of water. And I'm just going to quickly draw this because this is a really important concept right here. We're going to define it later, solvation, a little bit later in this virtual lesson. But that's what we have going on here. And then guess what's going to happen to the chloride? You got it. The H's are going to surround it from the water. So these H's, remember, they're not by themselves. They are parts of the water. But if you remember, they have this slight positive. This is slight positive, all slight positive. And then that negative right there, that's attractant. That's how they actually separate. So real important concept. So non-polar covalent compounds such as methane and compounds of oil, grease, gasoline, they don't dissolve in water. So we've all gone by either the ocean area or maybe the intercoastal, or even in a driveway after a rain, you'll see this almost like a rainbow look on the surface. That's oil. And the reason you see it on the surface is because it cannot dissolve. It is non-polar. Water is polar. Water will dissolve polar substances, but repel and not dissolve non-polar. So when you talk about gasoline and oil, oil will mix with oil. You can take any type of oil and mix it together, add gasoline, kerosene, any of those things to it. Well, you can't put that in water and it will not dissolve. So like dissolves like is a pretty important term. You're going to write this a little bit later, but like that's real important. Like dissolves but like. So polar will dissolve polar and non-polar will dissolve non-polar. They are immiscible when you try to put them together. If you have a polar and non-polar, it's called immiscible. They will not dissolve. So a solution process. The water molecule is polar and with partial negatives. We talked about that. These partial signs, a partial around the hydrogen side and the delta negative around the oxygen side. That's how it breaks up the crystal. That's what I drew. It just surrounds it and pulls it apart. Think about how stable it is, and yet water can break apart any of these compounds. So if you put salt on a burner, you're going to have to get to about close to 600 degrees Celsius to melt that. Yet you can drop it in water and it pulls it apart. Very fascinating chemical process. It is called it's not a chemical reaction that takes place. It's just a physical change. However, it still has some properties that are similar because there is a little bit of energy that is required to do that. So solvation, I mentioned this before. So the process by which the positive and negative ions of an ionic compound be surrounded by the solvent's molecules. Solvation, please get that in your notes. And here you see a little diagram of what happened. Here is, in this case right here, if we're talking about KCl, right here is the Cl1 minus, and you can see the minus sign there, and all the white there is the hydrogen surrounded. And when you come over to this side here, this here is your K1 plus, and all the red, which is the oxygens with their delta negative, their slight negative charge. All these guys have slight negative, and these here have that slight positive. That's how it breaks it apart. Very fascinating how you look at that. So that's the process is called solvation. All right, here's what I was talking about. You can see this look here in this slide right there. And we've all seen that, whether it's on the road, a driveway, in intercoastal, in an inlet, in a dock, or something of that nature. We've seen that. So polar solvents such as water dissolve ionic compounds and polar compounds. I'd put a little asterisk by that, please. That's an important concept. Jot that down. Polar solvents dissolve ionic and polar compounds. Non-polar will dissolve non-polar. Very important. And here's what you just saw me write a second ago. Like dissolves like. That's an expression that can help you remember this. Like dissolves like. So that's really important when you talk about solutions and dissolving. So let's look at a checkpoint right here. Which of these compounds should not dissolve in water? So let's look here. So here we have HCl, we have C4H10, we have Ki, and we have NH3. So we think about like dissolves like. We have here HCl, so you have this molecule here that's going to have a slightly negative on the Cl side and a slightly positive on the H side. So that's going to dissolve. Ki, that's an ionic compound. That's going to dissolve. That'll dissolve. And now you have ammonia. So remember the structure of ammonia. So you have a nitrogen, you have unshared pair here, and you have your H. So this is not symmetrical, it's asymmetrical. So you have running right through here like so, a dipole moment. So check, polar, water's polar, it'll dissolve. So that leaves us only one thing here that is not polar or an ionic compound. So therefore that is your answer. It will not dissolve in water. And that's the process of how you think about these things. Now we're going to talk about electrolyte and non-electrolyte. So what does that even mean? So let's break this down. Why are ionic compounds called electrolytes? So let's define it. An electrolyte is a compound that conducts an electric current when it is in an aqueous solution in the molten state. So when you think about an ionic compound, think back all the way to chapter 7. I know it's been a while ago, but we talked about the crystalline structure. So if you had a block of salt, of NaCl, and you put electrodes on that, it's not going to conduct electricity. It can't, because there are no free electrons. And if you remember, that was a property of an ionic compound. However, if you melt it or dissolve in water, so molten is melted or dissolve it in water, it will conduct electricity. And that's a property of ionic compounds, and that's what an electrolyte is. An electrolyte is a compound that conducts an electric current when it is aqueous solution or in the molten state. So that's what an electrolyte is. So all ionic compounds are electrolytes because they dissociate into ions. So all of them are. Now, you may be thinking, wait a minute, there's some solubility rules that we learned about. Yes, true. Well, I'm going to talk a little bit about that in a second. All right, so let's look at here. So if you had a source of current and you place in this, right here, you see this little picture, and in that is, let's just say in that beaker right there was distilled water, pure distilled water. The current would not go through and that light could not light. It would not light up. If you added sugar, it would not light up. Sugar does not conduct electric. So if you added any ionic compound, even in a small amount, now it will. And that's why water is so dangerous when you talk about puddles of water, swimming pools, bathtubs, all those things, because they're not pure water. They are solutions that have dissolved ions in them and therefore conduct electric. So water is very dangerous when it comes to electric. So sodium chloride is a strong electrolyte. It's 100% dissociates in water. We'll talk about that a little bit more. And that's how it conducts and flows current. So when we think about mercury chloride, it's a weak electrolyte because it partially dissociates in water. Now think about this for a second. You see the light bulb here? It is not very bright, but it still has a little bit of a charge going to it. You might be thinking, wait a minute. I thought the solubility rules said that mercury chloride is not dissolved in water. So when we think about our solubility rules, we had chloride and it always dissolves. It's a halide, except there was 3 exceptions. So we have silver, we have lead, and we have mercury. Those 3 are the exceptions. It doesn't dissolve. But when you see it says does not dissolve, there's something we didn't get to learn yet, and we won't get to in this term. If you take AP, you'll learn about this, the KSP, the solubility constant. The solubility constant is very low, but a small amount does dissolve. And that's why even these that are said to be non-soluble in water still will conduct a current. So they are called weak electrolytes because only a small amount dissolves. Hopefully that helps explain that. So when we talk about glucose, it is a non-electrolyte, and that's sugar. Glucose is another name for sugar, C6H12O6. You're going to learn a lot about that in biology next year. So if you drop that in the water, notice no flow. And I did this in the demo in the class. So what is a non-electrolyte? Is a compound that does not conduct an electric current in neither aqueous or molten state. So real important. So please make sure you get this into your notes. These definitions are really important. So if you have to pause the video, please do so to get these terms. So some polar molecule compounds are non-electrolytes in the pure state, but become electrolytes when they dissolve in water. This change occurs because such compounds as ionize in solutionize, they ionize. So how is that? By solvation. We just talked about that. The water surrounds them and pulls them apart. So ammonia, it is not an electrolyte in the pure, and this is a molecular compound. It's not an ionic compound, but it's a polar molecule. But this right here is the base of acid and bases. And we're going to touch a little bit on that the last 2 weeks of school, is acid-base chemistry. It's very important. And this right here is the base. Right here is a base, and water is acting as an acid. It donates a proton here and then becomes the conjugate on the other side. So we'll talk about those terms towards the last 2 weeks of school. So not all electrolytes conduct electric current to the same degree, and we mentioned that. We talked about mercury chloride is a weak electrolyte, and we talked about potassium chloride is a very strong electrolyte. So let's define that right here. So please get these into your notes. Both of these terms right here are very important. In a solution that contains a strong electrolyte, all or nearly all of the solute exists as ions. So it dissolves all the way. The only way it would not dissolve would become if it became saturated. So hopefully you remember that term. Saturated means it has all of the ions dissolved in it that it can hold at that volume and temperature. And then you have a weak electrolyte, conducts electric current poorly because only a small amount dissolves. Silver chloride would be one. Silver chloride, we did the lab where we dropped the silver nitrate into the sodium chloride, and you saw that white precipitate form. Well, even though that precipitate formed, we still have a small amount that is dissolved in the water, so it's called a weak electrolyte. So it conducts poorly, but nevertheless, it is still conduct. So please remember this. Water is an excellent conductor of electric. You never want to play with electric and water because it's very difficult to have just pure water. The only way you're going to get pure water is if you distill it and take it right out of the container that it's in. For example, distilled water you bought at the store or I've had in the lab. That's pure water and therefore doesn't conduct a current. But any other water, whether it's a puddle, it conducts because there are ions in it. So our bodies, they need electrolytes. So that's why we need salt and we need other things like potassium ions because of what's called an action potential in our cells. And it carries these impulses, whether it's nerves or muscle movement or our heart beating, all those things require electrolytes. So if you become dehydrated, now the electrolyte become imbalanced, they become low, and now you can't function properly. That's why dehydration is very, very dangerous. So when you exercise, you lose a lot of water and electrolytes through the sweat. Notice the salty salt that comes through your pores. So that's electrolytes. You got to replace that. And that's why Gatorade and other sport drinks are really important to drink while you exercise, especially if it's hot outside. So now let's go back to that case file. Pickles contain table salt. Why can current flow through a pickle, causing it to glow? Well, we just talked about that. So the electrolytes conduct the current. And salt is the main substance, the brine solution that they place pickles in. It's a cucumber that they drop into this brine spiced up solution that has a lot of electrolytes in it. And so therefore, that is why it actually can conduct, because it has electrolytes in it. So, checkpoint question. Explain why you must be extremely careful when using electricity near a swimming pool. Now, we talked a lot about that, so please, this is very important. Not just a swimming pool, a bathtub, a sink, any of those things. Very dangerous when it comes to deals with electricity and water. Why? Because, for example, a swimming pool is chlorinated. Chlorine is Cl-. That's an ion, and now that will allow electric current to flow, and that's why it becomes a shock hazard. All right, that's it for today, ladies and gentlemen. So we're going to pick up here on Monday and talk about hydrates and calculating percent composition. So these are some things we've done previously and we're going to review them. So thank you for watching. Enjoy the weekend, and I will see you on our virtual lesson on Monday. Go in peace.